All right, so question 4 asks us to use a Punnett square now to show the probability of two parents having either a male or a female child. So in the case of a mother, what are her two sex chromosomes? Great, X, X. In the case of a father, what about his? X, Y. Now if we represent as the possible chances of offspring, and we represent each, in this top left box it will be, very bad pen, XX. In the box to the right of it, it will be XY. And then if we repeat down the bottom, it will again be XX and XY. So these boxes in here represent a percentage chance of offspring. Now, in this instance, what is the percentage that there is a male versus a female child? Male? What's the percentage chance? 50%. Great, 50% male. And what about female? 50%. So this happens every single time, okay, fertilization occurs. There is a 50% chance, roughly, of male versus female. And this is why. We can do the math, right? So what is a sex-linked gene? What's a gene to start? What is a gene? A section of DNA? Oh, it's a section of DNA that, what? Codes for a trait. So what do you think a sex-linked gene might be then? Ooh, not codes for gender, but it's a gene that is found on the sex chromosome. So, describe what a sex-linked gene is. Number one, it is a gene found on the X or Y chromosome. That codes for a particular trait. All right. So far in this lesson, we've determined 50% chance of male, 50% chance of female. We've also determined that a sex-linked gene is a gene found on the sex chromosome, so either on the X or the Y. So in theory, there are going to be some diseases that only who can get? Only males. Okay. And in theory, there's going to be some diseases that are more likely to be seen in males than in females due to them only having one X chromosome. Yeah?
Since the male chromosome one's shorter than the others, does that mean it's less likely to become a boy than a girl?
No. So the size of them is irrelevant, is one way of putting it. It's more to do with the fact that it's the absence of the X. Okay? So when we have a look at a particular example now, and this example is something known as Duchenne muscular dystrophy. It's basically where the muscles waste away. We can have a look, and there's a few different genotypes. So I want you to note here, yesterday we were representing everything with the alleles like A or A. We're doing the same thing today, except now we're putting it in the context of the sex chromosome. So I'm going to use my highlighter here just to point out an affected male can be one thing, because Duchenne muscular dystrophy only affects the X chromosome. Notice how it doesn't jump onto the Y chromosome at all. So when we're looking at Duchenne muscular dystrophy, it must be what kind of trait if we've got a little d there and that's affected. Great, so we know that it is a recessive trait. What then about an unaffected male has capital D, okay? Now, is there any chance of a male being a carrier or being heterozygous? Can a male be a carrier for this trait? No. The reason is it is only found on the X chromosome. Notice how there is nothing on the Y chromosome because the Y chromosome is different. Females, on the other hand, okay, can only be affected if they have 2 copies of the recessive allele. So much the same as what we spoke about yesterday. Females can also be a carrier for this particular condition. Because females have how many copies of the X chromosome? 2. So they have how many alleles for this trait? 2. And then the final variation is you've got another unaffected female who has 2 copies of the dominant allele. Yeah. Great question. So some of the traits that we find in humans are still carried on those sex chromosomes. Now, while the X and the Y do determine the sex, they actually have a number of other genes on them as well, which are important for development. Okay. So, when we have a look down here, okay, here's a worked problem basically. And again, it states X little d is going to be the muscular dystrophy, and X capital D is going to be a normal allele. So we can now see in this instance if a parent was crossed. And here's the really important part. What kind of male? What kind of male? I've highlighted it in green up the top right. What kind of male is this? Is this affected or unaffected? Great, so an unaffected male, apologies, okay, is crossed with what kind of female? Affected or unaffected? Unaffected, but is she a carrier or is she not a carrier? Carrier, because she's got the dominant trait masking it. If we have a look now at the children, okay, what do you notice about the children? I'm going to use a colour here to highlight. Notice in males, 50% of the population is a male, and then 50% of the population is going to be female. Yeah? We happy with that? And then when we look at the traits themselves, right, if I go back to this one here, there is a 25% chance or a ratio of 1 unaffected female with the genotype of homozygous dominant. There is going to be 1 heterozygous carrier female. There is going to be 1 unaffected male. And lastly, there will be 1 affected, there will be 1 affected male as well. All right. So is the female that's heterozygous affected? No, because it's masked by the dominant trait. Okay, good question. So this one here, notice how they've then done ratios. So if I just switch this to like a pink pen or something, the genotypic ratios here, we have a ratio of 1 to 1 to 1 to 1. Now here's where people lose marks, right? It's really easy to lose marks on these questions because instead of writing X to the D like that, people will forget about the rules for sex linked, and what do you think they're going to do instead? They're going to write something like that. That is going to represent an autosomal allele. Instead, what we want to get into the habit of now, if it's a female, it's heterozygous like this, it is going to be XX. I always start by writing my chromosomes. Notice a little gap in between them. And then after, I will write my alleles just up the top. Similar to in math, if you're doing like x to the power of 2 or something like that. You're going to put it up the top like a, what's the name for something that goes up the top? I'm forgetting. Indice. There we go. So, when we have a look, here's the final thing before we actually get to a proper example ourselves. There is a 50% chance of having a son, and the probability of having a son with the condition is also 50%. So the probability of having a son with the condition must be 25%. Because if there's a 50% chance of 50%, it's going to be 0.5 times 0.5 equals 0.25. Okay? Okay. The easiest way for you then is simply going to be looking out of these 4. So if I'm looking at the cross up the top right again, out of these 4, how many are an affected male? 1. Only this individual. 1/4 is the same as what percentage? 25%. That's the other way you can do it. Yep. So, let's have a look now at some genotypes. We're going to practice genotypes together. So, in humans, this is a real example again. Is anyone in the room red-green colourblind? And I've been really doing your head in with my highlighting in red and green. win, okay? So, red-green colour blindness is an inherited condition in which both sex-linked and recessive. So notice in the question how it's told you. Number one, it's sex-linked, and number two, it is recessive. This is similar to your tests, okay? Your tests will try and guide you down the line of what the condition is. So, they have given you an allele. So what does that mean for you? It means that you must use the letter B. And this allele is carried on the X chromosome. Hint for you, we don't ever talk about Y-linked traits. We only talk about X-linked traits. Do Y-linked traits exist? Yes. Do you need to know them? Not in high school. Okay? So forget about them. When we're talking about a homozygous dominant female, the thing that I'm going to start with is that word female. This means that I need to write how many copies of the X chromosome? 2. So let's start by writing 2 copies of X, and I've left a bit of space in the middle for them. Now, homozygous dominant. What is this going to be represented as in our genotype? Capital B, capital B. Very good. Next, we look at another female. So again, I start by drawing my 2 X's. And now I have a heterozygous female. That is the same as saying a what kind of female? A starts with C? Carrier. Okay, a carrier, because this female is unaffected, but they carry the allele for red-green colour blindness. Lastly, we have a female once again. XX. This female is homozygous recessive, meaning little b, little b. So when we look at these individuals, let's start up the top once more. So this individual up the top, are they affected or unaffected? Unaffected. The individual in the middle, are they affected or unaffected? Unaffected. And this individual down the bottom, number 3, are they affected or unaffected? Affected. Very good. Which one is the carrier? This one here. This individual is a carrier. Unaffected, but they carry the trait. So, the Y chromosome does not carry a colour blindness gene. Males can only have 2 possible genotypes. State the phenotype. Okay? There's only 2 genotypes. And again, the reasoning here is either dominant or recessive. They only get 1 copy. So when we look at the dominant allele here, what is going to be the phenotype? What are they going to show? Will they be red-green colourblind or no red-green colour blindness? Great, so we could either write no red-green colour blindness or normal vision. Okay? You could write unaffected, but then what's the trait? You need to be specific. Right? So in our next one, the male is affected, so we would write red, green, colourblind. Are there any questions so far? How are we going? Is this like flowing on nicely from yesterday? We're just gradually expanding? Yeah? All right. So, here's where we get to the fun. If a colourblind man, so I'm going to highlight this in one colour. A colourblind man marries a woman who is homozygous for normal vision, what is the probability of the phenotypes and genotypes? This is the same as what we were doing yesterday, everyone. So what am I going to start with here? What is the very first thing that I'm going to do?
It's x little b y times x big B, big B.
Great. So we can figure out, based on the man here, something that I like to do every now and again is before I even get to my cross down here, I can actually annotate this diagram up here. Now you'll notice there's not much space, but a colourblind man only has 1 copy of the X chromosome. And in order to be affected, he must have the recessive allele, so X little by. And we've been told a woman, so XX, is homozygous for normal vision. And as we've done above, homozygous for normal vision is going to mean capital B, capital B. So the very first thing that we need to do is a cross. And so this cross is going to be this colourblind man, so X little by. And here's a tip for you all. You know how we've been doing a cross with an X there? make it really small so that it's not mistaken for an X chromosome now. Because what we then get to on the other side is female, right? And this female is homozygous, so capital B, capital B. So step one, we've done our cross. Our next step, what do we need to draw? Punnett square. So let's draw a Punnett square together. My advice to you is give yourself a little bit of extra room when it comes to drawing them for sex-linked, because we've got a little bit more to fill in. All right. So when we're looking at this one, I'm just going to follow the trend that we've been doing here, and the male is going to start with the XY and the female XX. I always start with the chromosomes and drawing them, just so I know exactly where things are going to go. So in the case of the male, it will be X little b. Is there anything on the Y? No, never anything on the Y for all of high school. When we then look at the female, so XX in the left-hand column, it will be capital B, capital B. So now all we need to do is what we've been practicing in prior lessons. We need to fill in the Punnett square. So I'll do the first box for you. X, X, okay? But what's the rule here? I have one capital B, I have one little b. What am I going to do? What comes first? Always the capital. So capital B, little b. X, Y. What X is this male going to inherit potentially? Capital B. Good. It's coming from over on the left-hand side. Up next, XX once more. And again, it will be another heterozygote, another carrier female. And lastly, this male will be affected or unaffected? Unaffected, capital B, coming from the mother once again. So, what we now need to move on to is calculating the probability of each phenotype and genotype. So, genotype, phenotype. In terms of this genotype, how many potential options are there for us? 2. There is a 50% probability of X, capital B, X, little b, and a 50% probability of X, big B, Y. So what are the odds now? If we were to calculate the probability, what am I going to say for the phenotype? You could. But what are we going to add now? What's the extra step? What's something that is different about these two other than affected or unaffected? Male and female. So what are we going to say about this one here? So there is a 50% chance for, great, unaffected female. Sorry, screw this one back in. 50%.
So we can write unaffected here though, but not
Well, technically you should be writing normal vision. I'll put that in brackets next to mine. Sorry, that's bad practice from me. Normal vision, female, and 50%, what?
normal vision.
Great.
Do you have to write the female as like a carrier? Doesn't it just have the two dominant ones?
You don't have to write that they're a carrier, because with the phenotype we're looking at what we can see. Yeah, good question. So when we're talking about this one, if I then asked you, what is the percentage chance of a female who is normal vision? What is the percentage chance of a female?
50%.
But now I'm just restricting it to just females. So if I said females who are normal vision, what percentage of females would be normal vision? 100%, because all females are normal vision. What if I said, what is the chance for a male who is normal vision? The answer would be 100%. What about for a male who is red-green colorblind? 0%. Okay, there is no chance, no probability for that. So I want you now, okay, to have a go at this next example by yourself or with the person next to you, I don't mind. If you get a little bit stuck, it's okay. We're going to go through the answer in about 3 minutes. Okay, 3 minutes time, we'll go through the answer. Right, so a woman with normal vision. So we've got to start here. Woman with normal vision whose father was colorblind. Okay, father was colorblind. I've kept them in the same color to show that they're related to one another, right? Next up, a man with normal vision. So, what is the chance that their firstborn child is colorblind? Now, their firstborn child has the same chance of being affected as their second child, as their third child, as their 32nd child, okay? That is quite crazy, I will admit. But there is the same chance no matter which child it is. So, what we're going to start with now is a cross. What is our cross in this instance? So the easiest one to do is a male with normal vision. A male with normal vision will be X, big B, Y, crossed with a female. Now this female has normal vision, so we know that she must have one dominant allele. But this question has given us some extra info, and it said that the father was colorblind. If the father was colorblind, what must this daughter have inherited? The recessive allele. So this mother must be heterozygous. We now construct our Punnett square for this particular instance. We fill in X capital B Y, X capital B, X little b. We then do our cross, so X, 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 Y, X, Y. And what I'm going to do is I'm going to fill in my letters here. So big B, big B, big B, little b. As we're going, can you mark yours? I want you to mark yours on a square by square basis. And in the case of males, big B, little b. Now, the question has asked, what is the chance that their firstborn child is colorblind? So as some of you have argued, do I need to write out genotype and phenotype? The answer is no. Should you anyway? Yeah, okay. And the reason I say yeah, and the reason I'm like you should do it anyway, is it's good practice and all you're providing yourself with is more information, right? So when we're looking here, the potential genotypes, I'm going to represent them as a ratio, okay? And in this ratio, how many potential options are there? 4. So it's going to be a ratio of 1, X big B, X big B, 2, 1, X big B, X little b, 2, sorry, I'll scroll over, 1, X big B, Y, to 1, X little b, Y. Well, this one is just easier. If I'm doing it as ratio, because some people were struggling with that yesterday, but you could also do it as a percentage. You could also do it as a fraction. So the percentage for this one would be 25% each time, okay? Or the fraction would be 1/4 each time.
What if in the test they ask you to do a ratio?
Then you do a ratio.
How do you do a ratio?
Well, in this case, there is 1 part or equal odds. So it'd be 1 chance of this one happening to 1 chance of this one happening to this one to this one. We'll talk more about that in a minute, okay? But for now, what are our possible phenotypes? We have, out of the female population, what is the chance that they are unaffected?
100%.
Great. So 100% of females will be unaffected. But in this instance, because females make up 50% of the total population for the child, it will be 50% female unaffected. Yes, good, thank you, good pickup. It will then be 25% chance of a male with normal vision. And lucky last, there is a 25% chance of a male with red, green, colour blindness. There you go.
I just said colorblind.
So, when we have a look at this one, it then continues on because we're not done. We haven't stated the chance. So I'm going to include this one here, so therefore, math sign, okay? Therefore, there is a 25% chance the firstborn child is colorblind. Okay. So this one here, that is a natural progression that you could get in a test scenario. Now what I'm going to get you to do, we've got about 15 minutes remaining in this lesson. Okay. I'm going to get you to have a go. There's not as many pages as there were the other day, okay? Just down to page 39, have a go at 7, 8 and 9. When you're done with that, because I anticipate you will be done with that, you will remember that yesterday you only completed up to page 33, so you finished up to the vinegar fly. You're going to then have a go at the remaining 3 pages.